Hello. So last week we talked about how psychology is a science as well as writing about APA. This week we're going to get into some statistical relationships. So if you've taken Psych 42 before, if you've taken statistics before, these should be relatively familiar to you. But since this is research methods, new day, who dis? So we're going to start with getting into discussing variables as well as central tendency as well as variability. So this is a pretty heavy, or at least there's a lot of stuff we're going to cover in this lecture. However, these are things that you guys should be relatively familiar with. So starting off with variables, there's two distinct kinds of variables that we're really going to focus on in this class. Those are categorical and quantitative. So just as a little overview, a variable is just something that could change. That could be the weather. So right now it could be smoky as all hell, or it could be sunny because it's, sunny. It could be cold, it could be whatever, but the weather can change, the temperature can change. So it could be 76 degrees or it could be 96 degrees, what have you. Number of hours of sleep you get each night, that changes. Eye color, that varies between person to person. And just anything that can essentially be different is a variable. So with quantitative variables, this is where we assign a number to an individual, and this number is representative of a value of some sort. So for example, your height, if you are 64 inches tall, that's me, I'm 5'4". If you're 64 inches tall, that represents that you are 64 inches high, or above the ground. The number of siblings you have, that's also a quantitative variable, where you have, if you're an only child, you don't have any siblings. If you got a big family, maybe you have 6 or 7 siblings or what have you. Ratings on a Likert scale. So if I were to ask you a question of, answer these questions with a 1 to 5 scale of how much it applies to you, those numbers that you provide would be a Likert scale. So as well as a quantitative variable that we can analyze later. So my kind of cheat to distinguish a quantitative variable is if calculating the mean of it makes sense, then it's quantitative. So if I were to give everyone a 10-question survey on a 1 to 5 scale about your depression levels, well, you answer all 10 questions, and then to get your depression score, as opposed to looking at one individual question, I want to know your overall score with those 10. Maybe I add them all up, or I can find the average of them. Either way, it works. But I find that depression score for each individual person. And then for the 40, 30, 55, however many people, it doesn't really matter if you're calculating average, I can find the average depression score of our class or of Fresno State or whoever it is that we're sampling. I can find an average and it makes sense. The average depression score is, if it's on a 1 to 5 scale, oh, maybe it's 4.6 or maybe it's 3.2 or whatever. If I were to ask you guys, how tall are you in inches? So 64 inches, maybe someone's 72 inches, maybe someone's 50 inches, whatever. We can find the average height of our class and say, oh, we take all of our heights in inches, add them up and divide by however many people there are, and then say, oh, okay, the average height of our class is 67 inches or whatever. So that makes sense to calculate the mean for those. Times where it doesn't make sense, and this is why I kind of think of it as a cheat, is with categorical variables. So this is when you're assigned to a category or a group as an individual. So if I'm going to ask you what classes are you taking, or what class are you in, well, this is 144. So you would say, oh, I'm in Psych 144. And where taking the mean or the average of Psych 144 doesn't make sense. Oh, what's the average of 144? I don't know how to answer that. How do I find the average of, a class where it's just looking at what it's called, like Psych 144? What's the average of Psych 42? I don't know. The average what? I need a quantitative variable to calculate average. Right now, you're just giving me a group. a category of individuals, I need more to that. So when you're not really able to find the average, again, this is my quick and dirty method of kind of distinguishing between the two. When finding the average doesn't really make sense, like, oh, what's the average of blue for eye color, let's say. It's like, so right, that would be a categorical variable. And these are I feel like these are fairly easy to distinguish. So if I were to ask you for eye color, you either have brown eyes or blue eyes, possibly green eyes, or my grandmother actually had hazel, or I think they were like hazel eyes, but one of her eyes had like a speck, or like half of it was blue or something like that, or oh God, I don't remember exactly, but she kind of had a distinct eye color. And so she can't really fit into the brown category, but she can't really fit into the blue category because she has a little bit of both. But in order to fit in a category, she would have to be categorized as other. And unfortunately, this has a lot of negative stigma for people who don't really fall into traditional binary standards, be it for gender between male and female. There's obviously a lot of wiggle room with that. Ethnicity is also a big one. It's hard to really, considering that we are in fact a land of immigrants, it's impossible to find someone who is just strictly, oh, I'm just this. So it's hard to kind of categorize ourselves as one or the other. And oftentimes with categorical variables, to make it easier for analytical purposes, for analyzing it and finding statistical relationships, other makes sense, but it's not, it doesn't have a good stigma. So I understand it from a statistical standpoint, but as far as a we are human standpoint, But anyway, I digress. So categorical variables, you're in one group or the other. You don't really double count yourself, because that will be saying that there's more people. So if I were to say like, oh, there's 10 people and I'm asking, what's your eye color? And let's say you have one person has a brown eye and a blue eye. Well, let's say out of 10 people, 9 of them have brown eyes. Let's just make this easy. Well, if the brown and blue-eyed person, if the one that has one of each, if they say, oh yes, I'm both blue and brown, then when we add them all up, that would actually be 11 people because they've double counted themselves as having a blue eye and a brown eye. So unfortunately, they would have to categorize themselves as other themselves. So anyway, I'm getting way detailed about other and how much I find it irritating. But anyway, so now we have samples versus population. So we have an idea of the categorical and quantitative variables. One point with that is that categorical variables are not only groups that you fit into, like, oh, your eye color, or, what classes you're taking, or if you're a full-time or a part-time student, or what your occupation is, what your job is, whatever. Categorical variables can also be the variables that are manipulated in experiments. So that can also be, let's say that I'm going to give you an exam, and half of the class is going to take the exam in a loud testing condition, pretending that we're in normal face-to-face classes, because I realize, we're all at home, so we all have different environments that we're taking exams in. But let's say for traditional face-to-face classes, half of you guys, or traditional face-to-face testing methods, I should say. So you sit in a classroom, you have a piece of paper and a Scantron and you're doing a test. Let's say for half of the class, I put you in a loud group, a loud condition, a loud testing room where someone is, playing the trumpet and playing it rather badly at that. Maybe they're practicing and they're like in 4th grade or something, or just, honestly, it doesn't matter how old you are. When you practice the trumpet, you don't know what you're doing. It's probably not going to sound good. But anywho, so you have half of the class is taking the exam with someone practicing the trumpet poorly. Then you have the other half of the class that is taking an exam in a quiet testing condition. So just the normal condition that we have when taking exams in a face-to-face setting. So just, everyone's sitting down quietly. Maybe you get the occasional sneeze and cough where people are like, oh, bless you. It's always so hush hush. But essentially you have that trumpet environment where it's loud and disruptive, and then you have the traditional, quiet, normal test setting. That would be a categorical variable as well. You're in one group or the other. You're either in the trumpet boys class where he's just tooting away, or you're in the, normal quiet testing condition. But I, as the researcher, manipulated that. I, flipped a coin and maybe said, you're going to be in this room where the trumpet guy is, and flip another coin for the next person coming up to me. And it's like, okay, you're going to be in the quiet condition or whatever. So categorical variables are oftentimes the things that are manipulated in experiments. Not always, but a lot of times they are. So anyway, off on my rant, apparently. Now, samples and populations. So when we're, as psychologists, as researchers, we want to know the relationship of things for a population. So it's one thing to just say, oh, half of my class took the exam in a loud trumpet condition, the other half took it in a quiet condition, a normal test, under normal testing circumstances. But, I only know it for the 40, 50 students in the class. I can't tell you if, what good this does. All I know is just these 50 people. As psychologists, we want to say, okay, so we want to expand it to a population, not just the number of people in our sample, but hey, overall, you're going to have trouble, not just these 50 students, but people as a whole will probably perform better in testing and on taking a test, but have better exam scores if they have a quiet testing condition as opposed to one where someone's playing a trumpet. We want to apply that not just to our sample of 50 or 40, but to, everyone, maybe all college students, if that's our population, or high school students, or whoever our population is. The problem with that, it's easy to say, well, why would we take samples? Why don't we just study the population? Then we don't have to make any guesses. Because with samples, we have to infer. We have to say, all right, I found results for these 50 people, 100 people, whatever, but I'm going to say that's how it is for the entire population that I'm looking at of college students or high school students or whatever. So it's like, well, why don't you just measure the population? Why take samples and waste our time and say, we think this is what's going on in the population and know what's going on in the population by measuring them? Well, the problem with populations is that they tend to be massive and really hard to keep track of, and it takes a long time. So if I were to give an exam in a quiet and noisy condition to all college students, if that was my sample, well, all right, so let's say I have to set aside about an hour or two to have everyone take this exam. That's how long the exam takes. Let's say it's an hour. All right, so I have to round up every single college student. Now, if that's just in California, that's going to be difficult. So let's make it with that. Let's just make it every college student in California. Now, I don't know exactly how many college students are in California. I'm probably going to say a couple million or at least a couple 100,000, but I'm going to say it's a couple million, maybe a million, a cool million or two. Again, I'm not sure. But let's say I want to gather all 2 million college students in California. Well, I have to find a way to contact them. So I have to know who they are, know how to contact them, and get them to come to me to take this exam for an hour in either a trumpet loud condition or a quiet testing condition. That's going to take a while, not only to find everyone, but to actually get them here. Let's say they're testing in Fresno, California. Well, what if they live in Humboldt and, they work full time and can't really just pick up and come to Fresno for no reason, or excuse me, for an hour-long test that really doesn't have much impact on their life other than I want the population. So it's going to take time. It's going to take money because I need to actually get us together all of the materials for these millions of people, and just resources as well. I need a room. I need time for myself to get this all together. And so by the time we get like maybe 100,000 people surveyed, it might take a year to do that. And then a year passes in college, suddenly some people have graduated, other people, new freshmen are coming in. So instantly the population of college students has changed. So now we got to start from square one and say, all right, well, what's the new population now? Let's look through the catacombs. Let's find everyone's emails and contact them. So we use samples because populations are just too hard to measure. So with the way we gather samples, there's two different methods. There's random sampling and there's convenience sampling. Random sampling is ideal. That would be the perfect situation. I'm going to tell you in psychology, it rarely, if ever, happens. So with random sampling, let's stick to our population of college students in California. Let's say that's our population that we want to randomly sample from. That's saying that every single college student in California has the same probability of being chosen to be in our sample. So let's say we're going to have a sample of 100, and with random sampling, all 2 million plus, or however many college students are in California, all 2 million of them have the same exact probability of being selected for our study. Again, that kind of involves us knowing their names, knowing their email addresses, or some way to contact them, and maybe doing a random number generator and seeing, okay, number 997,225, you have been randomly selected to be in my sample, and then do it again. Okay, number, college student number 572, you have been randomly selected to be in my sample. Well, and this is done through a number generator. I'm just kind of spitting out numbers right now, but this is done through a number generator. You don't just pick numbers off the top of your head. That's not really considered random. You need to have a computer do that. But anyway, that's not really possible, or at least it's not likely. Maybe if your population is super small, you can do random sampling, but yeah. So what we're going to do is convenience sampling. And this is what many, if not all psychological research projects use, convenience sampling, where the participants that are being collected for their sample, that they're gathering for their sample, are convenient for them. So either, you guys are going to be doing your final projects. The people that you have in your study are going to be, you can post it onto social media, Facebook, Twitter, Snapchat, Instagram, whatever, doesn't matter. But when you post things on social media, sure, yeah, you don't know who's going to do it, so that seems random, but there's a difference. Actually, it's convenience sampling, because who has access to your social media? Who has access to seeing things that you post on social media? Well, it's your friends, people people that are in your social circles, and that's not random. That's actually convenience, because that is people and only have access to you. So someone who lives in Humboldt and you've never been to Humboldt and don't know anyone from Humboldt, they don't have any probability of being in your study simply because they don't know you. So that would be convenience sampling. So operational definitions is also important in psychology and in research methods. An operational definition is how you define the variables that you're studying. So it's one thing to say, oh, I'm going to study depression in college students. Okay, so how are you going to measure depression is the question. Are you going to ask them on a scale? Are you going to give them a survey and, maybe the Beck depression inventory and say, hey, fill this out. And then that's how I'm measuring depression, your scores on this depression scale I give you. Maybe you have like in-depth interviews and maybe seeing how many, using qualitative data analysis, which is different from quantitative where we use numbers. Maybe you have interviews with them and then determine how depressed they are through that. That would be an operational definition of depression using qualitative methods. Maybe you study them. Maybe you observe them for, I don't know, like a 2-week span, and you kind of check for depressive behaviors and just kind of make a tally of how many times they display depressive behaviors. You need to define it. You need to say, it's one thing to just say, oh, I'm studying depression, but we need to know, okay, cool, how are you going to do that? Another thing you can think of is, I like using the idea of aggressive driving behaviors. So when people are driving and they get cut off, or someone doesn't know how to drive in general, just insert any reason why people suck at driving here, the way people react to that, let's study that. Let's study how aggressive driving behaviors are. So maybe we can observe people driving. So it's one thing, again, to say, oh, one of my variables is aggressive driving behaviors. How are you going to measure that? The way that we measure it is known as the operational definition. So am I going to give people a survey and say, check off all the behaviors that you've done in the last 2 weeks? Maybe it's flipping people off, driving over the speed, like way over, at least 15 miles above the speed limit, cutting people off, throwing things out the window, yelling, cursing, whatever, you know. Check all the ones that you've done in the last 2 weeks. Okay, that's one way to operationally define aggressive behavior, aggressive driving behaviors. Another way could be, again, kind of similar to observing people for the 2-week span for the depressive behaviors, maybe observing people driving. So maybe in a day, maybe we observe people driving for an hour. We're sitting in the car with them like a driving instructor, and just with our little notebooks, you know, we have the different activities or the different behaviors that we're looking for, like rude hand gestures or yelling or cutting people off, or, you know, we have a list of things we're looking for. And each time the driver that we're analyzing, that we're observing, displays one of those, each time they do that, they mark it down. That's how we are, that's one way to operationally define aggressive driving behaviors. So there's multiple ways to study the same variable. There's multiple ways to, I don't want to use skin a cat because I love kitties. I don't want them to be skinned, Jesus. But anyway, there's multiple ways to study one variable, and one way might be better than another, but just know that it's not one way or the highway, one way or the aggressive highway. So I've talked about operational definitions of variables. I've talked about categorical and quantitative variables, populations and samples. Now we're looking at the statistical relationships between variables. This is what the heart of research methods is about. You know, we have different ways to conduct research, but ultimately what we're doing is looking at relationships between variables. So there are two kinds. There's differences between groups, which is where we have one categorical variable with two conditions within it. So an example would be that the categorical variable of testing condition, or testing environment, I should say, where one condition is being in the loud trumpet room and the other condition is being in the, you know, quiet control room that we're used to taking tests in. That would be a categorical variable with two distinctions, or with two conditions, the quiet and the noisy. And then one quantitative variable. So we can do test scores. You know, how did you score out of 100 on this exam when you were in the quiet condition or in the noisy condition? That would be a difference between groups. We're comparing the average test score between the students who took the test with the trumpet boy and the average test score between the students who took the test in the quiet normal condition. Okay, so that is a difference between groups. Now, correlations between quantitative variables, this sounds really complicated, but essentially it's just correlation. It is looking at the relationship between two quantitative variables. So if I were to give you a survey, nothing is manipulated here, I should say, because of that keyword of correlation. So if I were to give you that depression survey I talked about earlier, where you just, you know, 1 to 10, on a scale of 1 to 10, and there's 10 questions and you answer them according to how you feel. And then let's say I want to compare that to self-esteem. I give you a self-esteem questionnaire, you fill those 10 questions out, or however many questions are there. And then I can find the correlation between those two. But I didn't manipulate anything. I didn't say, oh, you're a stupid human being and I hate you. Here, take the self-esteem questionnaire. I hope your self-esteem wasn't shot because I just insulted you. That might be a manipulation of self-esteem. You insult people or make them feel bad about themselves and then give them a survey talking about their self-esteem. They might have lower scores compared to that, to students who you're like, here, you look great today. You're really sharp. You know, you're probably like one of the smartest people I've ever seen come into this room right now. Take the self-esteem survey. That seems more like a manipulation. We don't do that in correlation. So it's just take the self-esteem survey and then take this depression survey. Have at it, have fun. We didn't manipulate anything on how they're supposed to respond to these surveys. So correlation between two quantitative variables, there's no manipulation there. So here's a practice for you guys. I want you to generate 3 examples of comparing differences between groups. Again, that example that I used was looking at, you know, comparing the test scores, the quantitative variable, between students who took the test in the loud condition or the quiet condition, those loud and quiet conditions are the two conditions of the one categorical variable of testing environment or room that you're in, or whatever you want to name it. And then 3 examples of correlation between quantitative variables. So again, that is just comparing depression scores on a survey that I give you to self-esteem scores on a survey I give you, and seeing how those 2 variables of depression and self-esteem are related. So go ahead and come up with some examples for that, write them down, what have you. If you want me to check over them, if you're unsure if you're on the right track, feel free to send me a message on Canvas, but just kind of generate some examples from them of these. Okay, so we talked about the difference between groups and the correlation between quantitative variables of the 2 types of statistical relationships that we have. Now let's measure the strength of these. So, you know, how do we know if there's a strong relationship between these 2 variables? Or how do we know that there's a big difference between this group and the other group? Well, it's through measuring the strength. And to do that for differences between groups, again, that, you know, that example of differences between groups is the test scores between loud and quiet testing conditions. We use Cohen's d for that. So that is, Cohen's d is looking at the number of pooled standard deviations that separate the means of the groups. What this means is that you're going to take the pooled standard deviation of each of your 2 groups, which essentially pooled standard deviation is the average standard deviation. So, you know, we have our 2 groups who took the test in the quiet and the noisy condition. Each of them have a mean, yes, which would be representative of mean 1 and mean 2. And no, it doesn't matter which one you have as mean 1 and which one you have as mean 2. It's just, you know, it's subtraction, but it's either going to be a positive or negative number, but it doesn't matter. And then dividing by the pooled standard deviation. Well, let's say, you know, for each group, we have our means of the quiet testing condition test score average and the loud testing condition test score average. We need to find the standard deviation as well. Let's say both of their standard deviations are 2. They both have a standard deviation of 2. Well, the pooled standard deviation is the average standard deviation of the 2. So 2 of one group plus 2 of the other group, that equals 4. Divide by 2 is 2. So the pooled standard deviation is 2. Now, if one of the standard deviations was 3 and the other was 2, you just do 3 plus 2 equals 5, divide by 2. The pooled standard deviation is 2.5. So the pooled standard deviation, you're dividing that, or you're dividing the mean 1 subtracting to mean 2, and dividing it by the average standard deviation between the 2 scores, or the 2 groups, or the pooled standard deviation. Correlation between quantitative variables. To measure the strength of this, it's Pearson's R. So that's depicted by the strength, which is the number, and the direction, if R is positive or negative. Now, the positive or negative matters with R. That is telling you something. With Cohen's d, all it is, oh, I subtracted the big one first, or I subtracted the big one from the small one, or the small one from the big one. That's really the only thing that the negative or positive number in Cohen's d tells you. It's not really a big deal. But with Pearson's R, if you have a negative, it's not, I just did this, or, oh, it's interchangeable. It means the same as positive, so it's whatever. Nope, that's not the case with Pearson's R, and we'll get more into that later. So for the thresholds of strength, we have for Cohen's d and Pearson's R, they're a little different. So with Cohen's d, 0.2 is considered weak, 0.5 is considered medium, and 0.8 is considered strong. Keep in mind that these numbers of 0.2, 0.5, and 0.8 are how many pooled standard deviations away from each other these 2 groups are, the means of these 2 groups are. So if you have a Cohen's d of 1 and your pooled standard deviation is 2, you know, by finding the average between the 2 standard deviations of our groups, if your Cohen's d is 1, that means they are 1 pooled standard deviation away from each other. Or if your Cohen's d is 0.5, that means they are half of a pooled standard deviation away from each other. So if our pooled standard deviation is 2 and our Cohen's d is 0.5, then they are 1 apart from each other. Maybe one mean is 7 and the other mean is 8. Pearson's R, we are looking at a difference of scores in the sense of, we're looking at not so much the strength of the difference between them, but we're looking at the relationship. So this is representative of the number. Again, this is the strength. We have 0.1, 0.3, and 0.5. I need you to go. I don't want you to watch me right now. I can't focus with you watching me. Do you need something? Yes, but don't fill the entire plate with it, okay? Okay. Okay. So for the differences between groups, and again, that's just the strength. So what I just covered is the strength. That's not looking at the direction. The strength is only focused on the numbers. So actually, before I go into the graphing aspect of it, I want you guys to know that if your Cohen's D or your Pearson's R is negative, okay, and you have a negative, let's say your Pearson's R is a negative 0.5. I know that it's tempting to think that's weak because it's less than 0.1 because, oh, it's a negative number and it's negative 0.5. Wow, that's way less than 0.1. But don't fall for that. Don't fall for that. The number 0.5 is strong. Doesn't matter if that's positive or negative. When you're looking at the strength of Pearson's R, or for Cohen's D, I should say, when you're looking at the strength of any of these two measures of effect size, that's what this is looking at. Pearson's R and Cohen's D are measures of effect size. When you're looking at this and you're trying to determine the strength, don't let the negative stuff fool you. Don't let the haters get you down. Just look at the number. If you have a Cohen's D of negative 3.0, that is a strong as hell Cohen's D. It's still, you're looking at the number of 3.0, not 0.3, but 3.0. That is strong. Doesn't matter that it's negative, it's still strong. Same thing for Pearson's R, although you can't have a Pearson's R that's greater than 1 or less than negative 1. But if you have a Pearson's R of negative 0.94, which is, holy crap, almost a perfect negative correlation, then you would have a strong relationship there. So now that I've kind of covered that. Differences between groups. So Cohen's D, when we're looking at the difference between one group and the other, we use bar graphs to depict that. And this seems kind of natural, you know, it makes sense. So if we're looking at the overall class idea, so we take a measurement of how students are thinking a class is going to be, like how they feel about a class coming up, or maybe the, you know, how much they understand the topics in the class. We can give that survey to men and women, and we can compare the differences between groups. Again, this is cutting out a lot of the in-between for gender. I know that it's not just male and female. I know that there's trans men, trans women, intersex. There's a lot more than just men and women. But for the problem with that is that oftentimes there's not a large enough population, or when you take a sample, there's oftentimes like maybe you get one trans male, or you know, one person that's intersex. And for the sake of analysis, it's hard to have a group of one and be able to make accurate representations, be able to make accurate analyses that apply to the population, because that sample of one is so small. So we're focusing on the groups that would likely have the largest number within the two of men and women, just to clarify. Now, second, correlation between quantitative variables. So with differences between groups, Cohen's D, when we're comparing the averages or something of one group to another, we use bar graphs. Makes sense. When we're looking at the correlation between quantitative variables, when we're looking at, you know, correlation, we use scatter plots. That's what this is called, a scatter plot. And so we graph the score of self-efficacy here and risk-taking. So this person here, they had a score of, oh my God, does it really show it? Oh yeah. They have a score of about, I don't know, like 1.4, it looks like, on risk-taking, and about 2, maybe a little above 2 on self-efficacy. That each data point represents one person, one individual, and both scores that they got on the surveys that they were provided, or the variables that they took part in. All right, so I talked about direction of Pearson's R and strength of Pearson's R as well. So when we have To go to the extremes, let's look at perfect positive and perfect negative correlations. Perfect positive correlations, all of those dots that are in a scatter plot here, all of those dots are in a straight line and it's pointing upward. From left to right, it's pointing upward. That's a perfect positive correlation. For a perfect negative correlation, again, all the data points in the scatter plot perfectly line up in a straight line, except this time it's going from highest to lowest. So keep in mind that with Pearson's R, I know I mentioned that direction, the positive or negative value means something. Well, here's where I'm going to start talking about it. So with that, with a positive Pearson's R, you have, again, positive is anything greater than 0. So on this part of the spectrum I have here, as with Pearson's R, as one variable increases, so does the other one, or at least so does the other one tend to increase. With a negative correlation, with a negative Pearson's R, as one variable goes up, the other variable tends to go down. So they're actually going in opposite directions. So here you'll see for a positive Pearson's R, for that perfect positive Pearson's R, on the x-axis, the horizontal axis on the bottom here, the numbers keep getting larger. Let's say this is 1, 2, 3, 4, 5, all the way up to 10, let's say. And on the y-axis, the vertical axis, it goes 1, 2, 3, 4. You know, the further you go up the axis, the higher the numbers get. Again, with positive Pearson's R, with a positive correlation, as one variable increases, so too does the other tend to increase. So we have both of these variables increasing together. With Pearson's R, with a negative Pearson's R, it's the opposite. One variable is increasing and the other is decreasing. So this x-axis here, you know, the further right we go, the more it increases. So this value here, oh, this is 1, 2, 3, 4, 5. These are all values on the x-axis. But on the y-axis, it's decreasing. So obviously at the top of the y-axis, that's the largest amount. But as we go further along, it goes down, 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 down. So again, negative Pearson's R means as one goes up, the other tends to go down. Positive means as they both tend to increase together. Now, in terms of determining strength from a scatter plot, again, a perfect correlation, be it positive or negative, tends to be in a straight line. All the dots follow in a line and they're just like a straight line. The further apart the data points tend to be, the lower the strength is. So you see for this 0.5, which is still considered a strong relationship, you'll see that they are kind of huddled around here. We can draw an imaginary line about right there. And yeah, a decent amount of the points on the scatter plot are kind of huddled or together, huddled along that line, if we were to draw an imaginary line. The less and less, the weaker that relationships tend to be in Pearson's R, the more that these scatter plots tend to look just random. So if I were to take a shotgun, let's say, if I were to take a shotgun and shoot it at a wall, that would be rather scattered. You know, shotguns tend to just kind of, it's a shotgun effect. And the points that are in these scatter plots, or the, you know, holes that would be in my wall, they don't really follow much of a pattern. They're just kind of bleh. That would be a 0 Pearson's R, where there's not really any distinguishable direction one way or the other. It's just bleh. It's like, again, I took a shotgun and just fired it into a scatter plot and said, here's my data. That would be a weak, or if not even weak, a relationship that has actually no relationship. This represents two variables that have nothing to do with each other, essentially. Okay, so correlation does not imply causation. It does not imply causation. It does not imply causation. This is going to be a question I have on every single exam, and the answer is causation. Correlation does not imply causation. Okay, now that I've hammered that, again, we're not manipulating anything as researchers. When I was talking about the exam conditions, where you can either be in a quiet or a noisy testing condition, I assigned you those. I manipulated where you took your exam. Are you going to have a trumpet boy? Or are you just going to have a normal testing condition? With correlation, I don't do that. Maybe I'll give you a self-esteem and a depression questionnaire, but that's all. That's where my That's where my involvement ends. I just give you the materials and you provide the answers. So with correlation, we have two issues with it. So yes, we cannot imply causation, and there's two kind of things that go with that. So with directionality, if we were to apply causation falsely to correlation, directionality is saying, how do you know that which variable is causing what? You didn't manipulate anything. So where do you get off saying one thing is causing the other? So if I were to measure exercise and happiness, you know, how many minutes a day you exercise, and then I give you a survey of your that measures your happiness, and I'm not manipulating anything. I'm just, you know, you report to me, oh, I exercise 60 minutes a day or whatever. Again, I don't manipulate that. But the directionality problem with correlation is saying, well, if you're going to say, oh, happiness is exercise causes happiness. Well, how do you know that happiness doesn't actually cause you to exercise more? How do you know that it's not the more happy you are, that will cause you to be in a mood to exercise? And, you know, oh, I'm feeling good today. You know what? I'm going to take a jog, or I'm going to pump some iron or whatever. Or, you know, how do you know which is causing which? You don't know with correlation. That is the directionality problem. You don't know which came first, the chicken or the egg. You're just eating eggs and eating fried chicken with it. So third variables is the next issue with correlation. So it's hard, and these are problems that make it difficult to imply causation. So with third variables, these are things that affect changes in the two variables you're looking at for correlation that you didn't measure. Let me put that in other terms. So if I'm going to measure depression and self-esteem, and let's say that the lower your self-esteem is, the higher your depression tends to be. There's a negative relationship there. I don't know this for sure, but let's just say that's what happens. Well, I could say, oh, having low self-esteem causes you to have depression. But there is a lot of different things that contribute to self-esteem, and there's a lot of different things that contribute to our depression levels as opposed to just the other thing. It's hard to say self-esteem causes depression when what else is related to depression? Well, it could be your genetic makeup. Maybe you have you don't have enough serotonin or dopamine in your brain, and that's kind of influencing your depression levels. Maybe you've had a hard life. You know, maybe your maybe you've recently lost a loved one. Maybe you're stuck in quarantine and, you know, you're kind of getting a little down on yourself. I'm sure we've all experienced that to some extent. There's a lot of different things that contribute to the variable of depression. Same thing for self-esteem. And it's not like depression is the only thing that has something to do with self-esteem. Your self-esteem can depend on how you were raised. You know, if your parents were supportive of you, it can vary on how you look, perhaps. You know, the way you look definitely influences your self-esteem, especially in this garbage society where if you're not considered, you know, a certain thing, you're awful and a waste of space. Well, if you're being told you're a waste of space or that your life doesn't matter, then yeah, you might have low self-esteem as a result of that. So, not to get into a BLM rant, but they fucking do. Black lives do fucking matter. But anyway, I'm not, okay. I'm not going to get into that rant right now. But once we get to the ethics study, or the ethics lecture, the ethics lecture, I'm going to go on a rant about Tuskegee, and it's not going to be pretty. But anyway, so third variables are the things that contribute to the variables we're measuring in correlation that aren't there. So I know anytime I try to describe it, it sounds weird, but think of, you know, if I'm measuring GPA and your stress levels, and I say, oh, having high levels of stress causes you to have a low GPA. Stress isn't the only thing that contributes to how well you do in school. It could be your resources. Can you afford to go to school? Can you afford to buy the book? Can you afford to get materials to study? Can you afford to eat? That's kind of a big thing. If you can't eat, or if you don't have a roof over your head, chances are you're probably not too worried about your grades and more focused on, you know, basic survival. But I digress. So third variables are things that contribute to changes in variables that you aren't really measuring, but definitely do have an impact. So I'm going to talk about descriptive statistics briefly. So now we're getting into central tendency and variability. I mentioned at the beginning of this lecture that we're going to be covering statistical relationships, variables, central tendency, and variability. Well, now we're getting into central tendency and variability. So descriptive statistics is a quick way that refers to summarizing and displaying data. So tables and charts, that's descriptive statistics, as well as ways to quickly summarize them, like mean and standard deviation. Excuse me, I have the hiccups now, great. If I drink too much coffee, I start hiccuping. But anyway, so with displaying data, I showed you guys some examples of bar graphs and scatter plots. So those are descriptive statistics of the displaying of data. And then mean, median, mode, standard deviation, and variance, those are the ways of summarizing data. So I'm going to go over central tendency rather quickly. Again, this is a type of descriptive statistic where we summarize data. I'm sure you guys are familiar with mean, median, and mode. Median, mean, the average, adding all the scores together, dividing by the total number of scores. And mean is affected by large or small numbers that aren't in the general gist of the data set. So if I were to tell you to find the average of 1, 2, 3, 4, 5, and to find the average or mean, excuse me, of 1, 2, 3, 4, 5,000, there'd be a big difference in the averages between those two data sets. There would not be a difference in the median between those two data sets, though. The median, the middle, is still going to be 3, because you're just counting, okay, what's the, on 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5,000 or 5 million or whatever, the middle number is still the same. It's still 3. Boom. And the mode occurs most frequently. So again, if I were to ask you guys, how many of you are psych majors? If I were to ask the majors in this class, so psych majors, biology majors, chemistry majors, everyone's different major, fairly positive that the mode would be psychology majors. That would be the response that occurs most frequently. Variability is a little different. With variability, this refers to how much the scores vary around that measure of central tendency. So typically when we talk about variability, we're going to talk about standard deviation the most. And with standard deviation, we use the central tendency of mean. So with standard deviation, we're looking at the average distance that scores stray from the mean, the middle of the data set. Again, central tendency means where the scores tend to centralize. Where's the kind of middle point of the scores? And the mean is one way to measure that. So the closer all the scores are to the mean, the smaller the standard deviation. The more, if you have your mean in the center here of 10 or whatever, and you have scores of like 5,000, -52, 100 million, if you have those scores in your data set and your mean is like a 10 or whatever, you're gonna have a large standard deviation. But if you have a mean of 10 and let's say all your scores are like 11, 12, 10, 9, 9.5, 11.5, 10 again, you'd have a smaller standard deviation in comparison to if you have a mean of 10 and some of the scores are 5 million and 100 and 100,000 or like whatever, if it's all over the place like that. So standard deviation is the average distance between the scores. So all the scores in your data set, be it you have a data set that has scores that has 100 people, and so you have 100 scores, or 10 scores, 10 people, whatever. That's that. It's the average squared, or it's the average distance between the scores and the mean. With variance, it's the mean of the squared difference between the scores. So with standard deviation, it's standardized. To find standard deviation, you take the square root of variance. Variance is often a larger number because all of the scores have been, the differences between all the scores have been squared and added together and standard deviation makes it standardized to where it makes more sense. So that's why it's called standard deviation and not just deviation. So to kind of give you more of an idea of standard deviation, because I know a lot of times for students it's kind of hard to conceptualize. They might kind of get it, or they might kind of get it. I don't know why I used air quotes for kind of get it, but they might got it. Yeah. But here's an example. So let's say that you're on Instagram and you get a DM from someone, maybe someone you went to high school with, probably, because they always tend to be involved in these pyramid schemes. But you're approached in your, in your DMs by someone who wants you to be selling LuLaRoe, women's legging distributor. And so they slide in and say, oh, I love your style. Would you like to what did you say to making that style even better, girl? Insert emojis and stuff here. LuLaRoe earns our sales team an average of over $100 a day. And you're thinking, holy crap, that sounds awesome. I can always go for, $100 a day. Who wouldn't, why not? So that's what this person sends you. They just say, you can earn an average of 100, our sales team earned an average of $100 a day. Ooh, that sounds great. Now, what she's not telling you is the standard deviation of this data set that they're referring to that has the mean of over 100. The standard deviation is 323.14. Now, granted, she might not really give a shit about standard deviation nor know what it is, but let's say that this data set, her sales team average with over 100, the standard deviation of her sales team is 323.14. Now, should you follow up with her and be like, hey, sign me up, I want to sell some women's leggings, or should you not? What is this standard deviation of 323 telling you? Well, let's say that this is her data set. So for her sales team, each data point, each of these numbers here represent the amount of money that different salespeople earned in one day. So this first person earned $20 in a day, 25. The third person earned 18, the fourth 32, 35, etc., etc. One person earned $1,000 a day. Maybe they were sitting outside of a yoga studio and everyone wanted to get new leggings. I don't know. That person just got $1,000 of sales in a day. When you find the average of these, when you add all of them up, it's 138.78. So her statement of you could earn over $100, our sales team earned an average of over $100 a day. That's true. This is over $100 in a day, so that's accurate. However, the standard deviation being so high is actually saying, yeah, that's the mean, but with that standard deviation being so high, that means that there's people that are much higher than that mean and much lower than that mean. That standard deviation is saying there's a big disparity. Our data set isn't $100 and where everyone is earning around $100 a day. Our data set, just like it's saying here, that standard deviation is telling us, yeah, 138 is the average, but some people earn $20 a day, $18 a day. Other people earn a freaking $1,000 a day. There's only one person who earned more than $100, but that one person made the mean sound like, ooh, this is a good deal. I can earn over $100 a day. So they ruined everything. So when we remove that outlier, that person who sold $1,000 worth of leggings, the mean is actually $31. So, ooh, you can earn just barely over $30 a day. That's how much our sales team earns on average. But notice that standard deviation. Once we take out the outlier of 1,000, that standard deviation is much smaller. It's 11.59 as opposed to 323. So again, now our mean is 31, and we see that our scores are a lot closer to 31. I mean, yeah, 52 is, a little higher than 31, and 18 is a little lower, but that's why our standard deviation is 11.59. If our standard deviation were 0, then all the scores would be the same. So if our mean was 31 and our standard deviation was 0, that means everyone sold $31 worth of product in a day. There is no one who earns any more or any less. That's a standard deviation of 0, where there's no variability or no difference between these scores. But we do have that. And oftentimes we won't have a standard deviation of 0. I mean, you could, but it's probably not going to happen. So this 11.59, that's saying, okay, so we have a mean of 31, pretty much about 31.13, and our scores tend not to stray in very far with that as a standard deviation of 11.59. However, this isn't as catchy. You know, if we remove that outlier, which should be done statistically because that's an outlier that's really tilting the scales. That's really making our data a lot more skewed with a mean of 138 when only one score actually got close to 100. Well, actually, no, even our score, our outlier wasn't close to 100. It was super, like, it was almost 10 times higher than 138. So keep in mind that standard deviation tells you a lot about data sets. The smaller it is, the closer that your data set, your numbers in your data set tend to be to that mean. Again, this standard deviation was massive, 323, with a mean of 138. Well, our numbers weren't really close to that 138. Oh, none of these were, not even close. And this 1,000 was way above that. But 31, this is a lot closer. We have a number that's almost dead on to our mean, which at 32. So keep in mind that standard deviation is really important in looking at the variability. So if you have trouble with standard deviation or have heard the term, but you never really understood it, I hope this helped. If you need more explanation or need to, you know, a refresher or whatever, don't hesitate to contact me. I'm happy to explain it, happy to walk you through it if you still are having a little trouble. But that is our variables, central tendencies, statistical relationships, and variability lecture. So have a good day. I hope you guys all, you know, have a good rest of your week, and I'll see you. Like and subscribe.